Hello everybody, I am Felipe Toledo and I'm going to be presenting our work, Deeper Notions of Correctness in Image-Based DNNs, Lifting Properties from Pixel to Entity. The increasing capabilities of DNNs have made them widespread across many different domains. However, this system continuously exhibit failures that can lead to fatalities or discrimination. Therefore, it is necessary to check that these systems satisfy their intended properties. In the last couple of years, researchers have developed different algorithms to validate and verify if a DNN meets specified requirements. In a few words, these tools take in a property phi and a DNN n and outputs whether the property hold is violated or unknown. A property example in the autonomous vehicle domain can be adding noise to an image should not change the steering angle by more than 5 degrees. If we have an original image for which the predicted steering angle is 15 degrees, a violation can look like this, where we added noise to the original image and now the predicted steering angle is minus 15 degrees, having changed more than 5 degrees. Another example in the same domain could be adding snow to an image should not change the steering angle by more than 5 degrees. The original image and its predicted steering angle is 15 degrees, and a violation can look like this, where we added snow to the original image and now the predicted steering angle is minus 15 degrees. Another example, now in the domain of gender classification, can be changing the brightness of an image should not change the predicted gender. If we have an original image for which the predicted gender is male, a violation can look like this, where we change the brightness to the original image and now the predicted gender is female. To summarize, current properties are stated over the entire input. Our vision is to enable the specification of properties that capture the semantics of entities in the world, specify how they can change, and be supported by many VMB clients. Current methods can add noise or snow to an image and violate a property. However, in our vision, we want to define properties like the following. Changing the incoming vehicle type and color should not change the steering angle by more than 5 degrees. With this property, we want to change the track highlighted in orange for other track models and colors, and if the predicted steering angle of any of these new images differs in more than 5 degrees, then we have a violation. For the gender classification domain, current methods can modify the brightness of the image and produce a violation. In addition, we want to define properties like the following. Changing the color of the hair should not change the predicted gender. This property changes the hair highlighted in orange for other colors, and if the predicted gender of any of these new images change, then we have a violation. So to achieve the proposed vision, we need to overcome the following challenges. Identify entities. In principle, this could be done manually, but segmenting entities in complex inputs is difficult and time-consuming, and can take more than an hour and 20 minutes to segment one image. The second challenge is to determine entity transformation. We need to specify how the entities can change, and we need a way of doing it automatically without incurring in manual effort, for example, using photo editing software. The third one is the property encoding. Writing the specification is difficult as it requires defining the behavior of a system in a formal language that can be processed by different clients. Creating these properties at scale is infeasible if done by hand. Current techniques fall short in addressing all these challenges. Some of them are able to solve one but not the others. Therefore, with our vision, we want to solve the three challenges at the same time. To overcome all the challenges and accomplish our vision, we propose a new framework, EPROP-HEN. EPROP-HEN takes in an image and outputs a property specification. It contains 3 modules to solve each one of the challenges. The first one is the identification module. The goal of this module is to take in an image and the name of an entity that we want to target and output a segmentation map of that entity within the image. This step can be performed manually, but to do it at scale, our framework leverages recent AI-based detection systems, or allows to use custom detection system in case we want to segment entities that are not supported by the other models. The second module of our framework is the transformation module. This module takes in the image with the segmented entities returned by the previous module and a transformation function, and generates a DNN prefix that encodes the domain-specific transformation. The output is a DNN because tools can work directly on it and work as a symbolic encoding of how things can change. There are many ways of transforming the inputs. Different generative AI models can be used for this purpose, like Stable Diffusion, generative adversarial networks, and variation autoencoders, or we can develop our own custom function, like we did in our study that I will explain later. The last module of our framework is the encoding module. This module takes in the DNN prefix returned by the previous module, a precondition on the new DNN prefix input, and a postcondition on the original DNN output, and generates a property specification. In order to encode the property, the framework can support different specification languages like DNNP or PNNLib, or custom one designed for a specific tool. Having explained how the framework is structured, now let's jump to a feasibility study that we carried out. The main idea of our study is to explore what it takes to instantiate our framework and the insight that these properties can provide. We use the Fairface dataset, a dataset that contains photos of people's faces for predicting gender, age, and race. From all these prediction tasks, we choose the gender classification because we can define interesting properties. The DNN under test is a ResNet34 provided by the authors of the dataset, and we define the following properties fit. First one is gender is independent of skin color, and the second one is gender is independent of hair color. We instantiated our framework to generate the property specification. First, we pass an image, and the identification module segments the face using a pre-trained model for face and hair segmentation, and outputs a segmentation map of the face. Second, the transformation module uses the segmented image and applies our custom color function that essentially changes the color of the segmented pixel. The transformation module outputs a DNN prefix with 5 inputs, 4 of which are the color channels of a CMYK color map, and the 5th input is the intensity of the color. Lastly, we use the DNNP library to specify our properties since it is compatible with multiple PNB tools. And the encoding module outputs a DNNP property specification. This process was repeated for each image in the dataset, and we ended up creating over 8,000 DNNP specifications for face and hair properties that we check using validation tools. Doing this by hand would have taken around 500 person days. Jumping on the results for the property gender is independent of skin color, these are some of the counterexamples that we found. We can see that in all cases they have a smooth and consistent change in skin tone, and the color is still in the skin tone range. From the 8,000 specifications that we validated, we found that over 5% were violated. For the second property, gender is independent of hair color, these are some of the counterexamples that we found. We can see that in all cases the color of the hair changed significantly. This happened because we did not restrict the color to only be within a specific range, based on the assumption that anybody can dye their hair in any color. And from the 8,000 specifications that we validated, we found that almost 6% were violations. These results highlight the potential to define and check new types of properties that target different entities and go beyond the properties defined over the entire input. Each of the modules that I described have some remaining challenges. For the detection module, the challenge lies when a segmentation error happens. These errors have different implications depending on the BNB client that we use. For validation tools, errors are going to be false positives, but for verifiers, which can determine if a property holds, an error will mean providing false guarantees. Thus, we need to develop mechanisms that account for such errors. For the transformation module, complex transformation like changing the make and model of a car would require sophisticated mechanisms. We mentioned that different generative models can do the job, but adapting them to work at an entity level and making BNB clients support this generative models architecture is still a work in progress. Lastly, for the encoding, using a DNN prefix to encode transformation can provide flexibility for specifying nonlinear changes and increases the usability of the property specification by different BNB clients. However, crafting the prefix currently requires either manual encoding, as we did for the color properties, or either training or finding an off-the-shelf model that can handle the desired transformation. Finding ways of automating this process and encode other transformation is still a significant challenge. As a future work, we think there are two directions to explore. One is to add support for more sensor inputs, like LiDAR or radar, to validate the behavior of broader types of systems. And the other one is to enable property specifications defined over a sequence of input and outputs to validate the behaviors of more systems. Thank you very much for listening, and I hope you enjoyed the presentation.